So TempleOS runs in 64-bit long mode. If you know about segment registers in 32 and 16-bit, in 64-bit, the SS, CS, DS, and ES are all set to 0, and they have no effect. I think. Maybe you can do a privilege thing. I don't remember. I don't use privilege levels. Anyway, FS and GS can be used as, they're pretty fucked up, because when they created long mode, if you do an instruction like this, in long mode, that's RIP relative, okay? So what that means is you can load data that's within 2 gig plus or minus. 32 bits is 4 billion. So this is a 32-bit displacement. So it's RIP relative. So what that means is if your program is at, let's say, 3 at 12 billion, if your program code is at 12 billion, then this is going to be 11 billion to 15 billion. Okay, so we're clear. The normal addressing mode is RIP relative. So it's you subtract the RIP when you're making the instruction. So it's something like, in fact, I think some assemblers or disassemblers show that. Anyway, so here's where it gets interesting. Guess what? Guess what happens if you do FS? You guessed it. It's RIP relative. Now that does not make that makes no sense. This instruction makes absolutely no sense. Okay, this instruction is ridiculous. So what can we do about this? Well, we don't really want this mode, that's for sure. So what we do is instead we go to what if we set RAX to 0 and then do this? What if we say XOR Okay. Shut up, bird. Shut up, bird. I'm gonna smack you. Shut up, bird. So, shut up, bird. Shut up, bird. So, shut up, bird. 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 Okay, so I really wanted an extra general purpose register for my task. I really wanted an extra general purpose register for my current task, and so I made FS. The FS segment register holds the current task record. GS holds current CPU core record. Okay, so there must be an easier way. I don't know how you could. Anyway, they're basically general purpose registers that are very hard to use. I use FS and GS like general purpose registers that are very hard to use. In order to set, as a matter of fact, they're almost unusable. But honestly, I can't figure out any other way. You would have to store how would you do it with multiple cores? Anyway, as I think about it, surely there's a simple way to get. It's not so simple though. It's pretty hard to get a general purpose register. Anyway, I use them. What if there was a simple way to not use them? A replacement with memory. Is there any replacement? I can't really think of one. Anyway, is this it? Set GS, set FS. So you never called these. As a matter of fact, TempleOS is, a motorcycle. If you lean over on a motorcycle, it crashes. Well, if you change FS or GS, it crashes. It's a ring zero operating system, so it's like a motorcycle. Don't be stupid. Of course it crashes if you lean over on a motorcycle. Anyway, so FS and GS are the task record, and you have to set them with the model specific register. Right model specific register. You set the value of FS or GS with right model specific register. Now I built it into my compiler, accessing FS and GS. FS is my task record. We're going to trace the output of the compiler. So if here's what trace means. Count I64 in. Okay, so what trace means is it displays what it compiles. So it's kind of like Commodore 64, where you entered basic programs if you entered line numbers, or you entered basic commands if you did not use a line number. So there, what it did is it did a little bit of code to call the function, and then it counted to 5. So long story short, if we want to see how FSRIP is the that's where the R instruction pointer is stored in the current task record. So how did we get it? Okay, well, we set AX to 0, and then we accessed an offset from AX off of FS. So you have to be really determined to get it. As a matter of fact, I did a trick for in order to get the value itself. I learned this trick at Ticketmaster. I don't remember what it was used for, but as a matter of fact, sometimes it's convenient to make a record where the first address is a self-addressed envelope. The first address is a self-addressed envelope. Anyway, so that's what this has, is a self-addressed pointer. So when you do FS, the compiler has FS. Let me explain how this works. We might as well go through it from start to finish. So in there, TempleOS doesn't inline functions, but it has built-in functions. Okay, so as you may or may not know, as a matter of fact, you can say FS okay, you may or may not know that if you say directory, if you have default arguments, it has default arguments from C, and then I took it a step further and I made parentheses optional if you have no arguments. And so FS is actually a function. FS is a function. It turns out it's a built-in function. Let's see if we can find it. FS. FS is a function that returns a task pointer. And it's an internal function. There's about 100 intermediate codes. These are what the intermediate language is composed of. So let's take a look at ICFS. So find ICFS. So when it parses, we have O trace, or no, pass trace. Okay, whatever. Pass trace. Okay, so if we say FS RIP, this is showing us the intermediate code along with for each of the optimization stages. So it starts as a function call to FS, which is an internal function. Anyway, all function calls have a start and an end, and RAX is the result. I could be wrong. Anyway, and then it's a stack machine, so that gets pushed on the stack, It's not, well, anyway. We're abstract at this point, not registers. So it's on the stack. We push 138 on the stack. We pop the top two and push the result, which is the 138 plus RI plus FS. We dereference it, and that's the result. Okay, now as it optimizes, it discovers that there's it converts reduced instructions into complex instructions, and it immediately converted those three into a MoveFS. MoveFS is a complex instruction. So as a matter of fact, we're not really as a matter of fact, ICFS, you see, this is a different internal. If we look at our, if we look at, this is a list of all the intermediate codes. MoveFS is a different one. So as a matter of fact, there might not be any of these after a certain pass. I could be wrong. There's referencing, there's dereferencing, and then there's referencing. What if we say FSRAX? This is kind of tricky. Is this going to leave it? I'm just curious if it still uses the FS. Okay, now that time it kept it. So these, they diverge. Okay, so that's the address. Okay, so the FS gets coded as RAX and then self-address. Anyway, I was going to talk about. I don't feel like it. It gets converted to assembly code at the very last stage of the compiler. Machine code. It doesn't. Some compilers make assembly, so I'm told. Mine doesn't make assembly. It makes machine code. As a matter of fact, if you want to see where we code, we have little tiny sub instructions. This will put a 0 into RAX, and then we output some machine code, 8B4864. And guess what that is? 8B4864. That's it's 4 bytes. Okay. (6.4) is the FS prefix. 4.8 is the 64-bit prefix. 8B is move. I don't remember. I guess it's a. Isn't it a modern? Yeah, it's a. Well, we know what it is. I'm just trying to. I'm wondering why it's not more bytes. Obviously, we have the answer. Okay, modern, the 0 to 3F is indirect in RAX, and RAX is Okay. If you want to see, the modder is 0 to 3, 2 to 3F is indirect. Where'd he go? Oh shit. 0 to 3F is modder. Okay. This is what it was, RAX 0, 0, it's indirect 0. This is 0 to 3F, 40 to 7F, 80 to BF, C0 to C down here. 0 to 3F, 40 to, okay, 0, 0. Okay. Isn't that fun? That's fun.